Hello and welcome back to yet another video in this playlist that is deep learning projects. Now, of all the deep learning algorithm that we have created so far as a part of this particular playlist, this one that is GAN, Generative Adversarial Network, is where we'll be peaking. We'll be really going to push our limit and try to create some very exciting algorithm. What is GAN? If you're not already aware, there are two neural networks that we'll be designing. One is generator, another one is discriminator. In generator, we are going to generate the image based on the dataset that is being given to us, and we'll be dealing with fashion FMNIST data. That is the job of generator, that is to generate the fake image. What is the job of discriminator? Yet another neural network that we'll be designing, again trained on our existing training data of FMNIST. The job here of discriminator is to discriminate between the real images, that is existing images, and the fake images that is being generated by the generator. We will be training our model until the point where discriminator, beg your pardon, it is no longer able to discriminate between the real images and the fake images. At that point, we have successfully trained our model. With that, let us get going and see what the project is all about. Let me quickly name this as GAN FMNIST dataset. Now, this is not MNIST, this is fashion dataset. That is bunch of apparel that we'll be dealing with. So I'll just quickly call that as GAN and FMNIST. Again, in this particular project, we'll be demonstrating a CNN-based GAN applied to fashion MNIST dataset, a collection of 28 by 28 grayscale images of all the fashion items, things like, you know, uh, sneakers and jeans and all those things. And we will try to generate new images based on our existing images. So let me go ahead and import all the libraries that is going to be useful for us. Import numpy as np for numerical operations. Import torch, the core library for tensor computation and deep learning. Import torch.nn as nn. So it is importing the neural network module from PyTorch, providing the building blocks like layers and all other things. And you have import torch.nn.functional as f. This is going to import functional operation, activation functions, and all those things. Then I'm going to import the data. For that, I have to import torch vision. Then I will import torch vision dot transforms as t. It is going to import transformation utilities for pre-processing of images. Then you have from torch dot utils dot data import data loader for batching the data, and I'll also import subset for selecting portions of a dataset. Then I'll import matplotlib dot pyplot as plt. These are the libraries that will be importing. Then the next is to say device is equal to torch dot device. That is basically CUDA. If torch dot CUDA is underscore available, else CPU. And this is device. So what this is doing, that if CUDA enabled GPU is available, then set device to CUDA. If it is not available, then it is going to allow the CPU to be used as a computation system. So run that. As of now, I'm only in CPU, and I'll keep it this way unless we are not, we go into the GPU portion, will not be using it. So for now, I'm keeping it as CPU. later on in the uh, notebook, we'll see that this will be CUDA here when we turn on the GPU. Okay, now let us go to the data transformation and loading. Data transformation and loading. First things first, I'll have to define transform as a variable that is going to create basically a composition of transformation to pre-process the data. And for that, the first in line is t dot compose. Then inside this, I'm going to pass it in a form of list. This is t dot to tensor, t dot resize and 64, then t dot normalize, and for that I'll pass that as 0.5 to zero point 0.5. So let me explain what is going on here. Uh, this is creating the transformation to pre-process the data. T dot to tensor, it is going to convert the images from PIL format or the NumPy array to PyTorch, scaling the pixels values from 0 to 1. Resize 64, it is resizing the 28 by 28 fashion MNIST dataset that we have into 64 by 64 pixels, because what you have to understand that your GAN, it expects input size of 64 by 64 pixels, right? And last one here, it is going to normalize the tensor with a mean of 0.5 and standard deviation of 0.5. So this here is that. Then next is to load the data set. So I'll say data set is equal to torch vision dot datasets dot fashion MNIST. Root is equal to dot / data download equal to true. Then transform equal to transform. There we go. It's going to take some time. Okay, so it is done at my end. Now, what we have to do is we have to select the specific class, and we also have to create the data loader as well. So if you just look at the classes here, I'll say dataset classes. And if you see, try to print this, these are all the classes that you have. So t-shirt, top, trouser, pullover, dress, coat, and all that. Now, if you're wondering that how can I see this, don't worry, we'll do that as well. For now, you just understand that these are the classes, those are available to us. And then we have the images themselves. So maybe there's some certain image and the associated classes here. For example, image, it can be of t-shirt, thereby the class would be of t-shirt and top. Some other image, it will be of trouser, thereby the class is the trouser. So we have this label data. Now what I'm going to do here is I'm going to define a list of just 3 classes to focus on. You can create a list of as much as you want, but for us, I'm trying to keep it simple. And I'll say that I will just focus on classes to focus. It is trouser and maybe sneaker, and just one more. How about sandal? Sandal, it is sneaker. I'll say pullover. I think pullover, it is having capital P. There we go. Right. So this is the just 3 classes that I'm considering. Now I'm going to say I'm going to initialize an empty tensor to store indices of the images from these selected classes. So for that, I'm going to say images to focus is equal to torch dot tensor, and this should be capital T. Then I'll say that for I in range length of the list that you have created, that is classes to focus, basically 0, 1, and 2. For each of this range, get me the class index. It is going to find the index of the current class in the data dot classes. So I'll say class index is equal to dataset dot classes dot index, and that is classes to focus of that particular index. Now what this is doing basically is, if you pass in, I'll copy this, and if you just pass in over here like 0, 1, 0 here, let us say classes to focus, it is not defined. Is that so? We have defined it. Oh, we have not run it. I'm sorry. So we have to run this first. And for running this, let me run this. I think it should work. Yeah. So if you run this over here, you will see that you have this 0. What this 0 is representing? This is this trouser. So trouser in my classes here, it is at index 0 and 1. How about sneaker? Because this is at a later part. So sneaker, it is 2. Sorry, 1 rather. Trouser was 0, so this is 1. So the list that I've created, if I'm talking about sneaker, which by the way happens to be at index 1, then I'll get a index 7. Why it is 7? Because from here, 0, 1, 2, 3, 4, 5, 6, and 7. This is 7. So I'll remove this. This is just for explanation part. So I'm getting for that particular index, I'm able to get the class index from your original classes. Then I will say images to focus is equal to torch dot category. Then I'll say images to focus, comma, torch dot where. Then I have to mention that where the dataset dot targets is equal to class index. So wherever that index is matching, then I just that is it element index 0. Then this entire thing I will pass in, not required actually, but still I'll pass it as type torch dot long. Okay. Now this is, I know it can be a bit clumsy. So let me just write down formally what we have done. I have basically added class curly braces classes to focus, then that particular index, then I will say index curly braces class index, and you run that. It has given me an error, that is tuple object has no attribute type. Let me fix this. There has to be some problem here, I think. Yeah, of course. This here, we have to actually pass this thing as one more. Then this should work. And we have to remove this. There we go. So you can see that we have added the class browser again, the one that I have mentioned here. This is basically saying that it is at index 1, this is at index 7, and this is index 2. Now you can add in any other thing as well. Maybe you can take this, copy here, and make some changes. So I will just, comment this out over here just to explain. So instead of pullover, let me say that I'm adding a bag here. All right. And the sneaker, it is not a sneaker, it is a coat. Now you run that one more time. You see the coat, it is at index 4, bag is at index 8. So this is how it's going to. So whatever the list that you are going to prepare, it is going to give you the respective index in the original classes. This is what we have done. Let me comment this out and comment this over here. What we are going to do next is I'm going to transform to the data loader, because I want to take the entire dataset, then use the subset sampler to draw only from the selected classes. So for that, I will say that first of all, I'll say batch size, it is 100. And I'll say sampler is equal to torch dot utils dot data dot sampler dot subset random sampler, then images to focus. Thereby, this sampler here, it is only using the subset sampler to draw only from the images to focus, basically this tensor that we have created. Remember, this is what we have created over here. If you're not sure about this, again, you can just run this images to focus, which by the way was the empty here, empty tensor that we created, but that is no longer the case after we have basically concatenated using this for loop. So this, I'm going to take the only the sampler, which is important for me. Then I'm going to say that data loader is equal to data loader and data set, comma, sampler equal to sampler, batch size is batch size. And I'll also say drop last equal to true, and which basically is going to drop the, because the batches is 100. Now let us say in the last batch we do not have 100, we just have maybe 75 or 35 or whatever. So to skip that, to skip those last 75 and 50 or whatever value, we are going to basically drop them. We are not going to consider it, so that we have a batch size will be consistent with the 100. View some images. And for that, I'm going to say x, comma, y is equal to next, then iter, then data loader. All right. And then I'm going to create some plot that is going to be figure, comma, axis is equal to plt dot subplots 3, comma 6, then fixed size. So there will be 18 plot. This should be enough. 3 rows and 6 columns. Fixed size, I'll say that. So we have 6 columns. Thereby, I'll put 9 by 6. That is the fixed size. And I'll say for every index, comma, axis in enumerate axis dot, sorry, this is not axis, this is axis. Otherwise, this will take in built-in word. Axis dot flatten. So I'm going to flatten out all the axes, and that is going to first extract the image. So the picture that I have, that will be torch dot squeeze x data for that particular index. I'm going to undo the normalization, because remember, initially we have normalized all our images when we created this transformation. So standard deviation 0.5 and mean as 0.5, I have to unnormalize this or undo the normalization. So picture is going to be picture by 2 plus 0.5. And then I'll check the corresponding label for that particular dataset dot classes of that particular index. And lastly, dot I am show picture. Let me run this. If it is working or not, then I'll fix other things, because if it is not working, then there's no point of doing any further. Quite well, right? You can see all these images over here, right? So let me fix some of the things here. I'll say, first of all, put some text X and Y. So I'll say it is 14 by 0. Then I'll say I want the label that I want to put HA, that is the horizontal alignment, is center. Font weight is equal to bold. And I'll maybe put some color. I'll put that as color as red, and background color is yellow. Let me run this. Okay, quite well. Let me do one more thing. I'll turn off the axis. Sorry, this is AX dot axis is equal to, sorry, in curly braces, you have to put off. But I made a mistake actually here. I have to put this entire thing at the top. This should be over here. Okay, quite well. Right, maybe you can put the color at something else. You can put this as maybe blue. So that becomes much more readable. Right, so we have all this. Now, every time you run this, and I'll try to zoom out a little bit. Every time you run this, it is going to display a different set of images, right? So you can see that trouser, sneaker, trouser, pullover. Now, if you run this one more time, it's some different images here, pullover, trouser, pullover, and all that. Now, we have to create the classes for the discriminator and generator. So this is where the game starts really. Create classes for the discriminator and generator. Let me start with creating the classes of discriminator. First, I'll inherit everything from nn.module. Then I'll say def underscore underscore init underscore underscore self, that is the constructor that is going to inherit everything from the nn.module. And then we are going to add in the convolutional layer. So I'll write in everything, then I'll try to explain what we have done. So convolutional 2, sorry, not 2, rather 1 is equal to nn dot convolutional to D, and that is going to have 1 input, 64 output, then a kernel size of 4, a stride of 2, and a padding of 1. And lastly, I'll just put a bias as false in this case. Again, this is a tried and tested network that I'm creating. As I said, all this network you have to find out empirically. I already have spent enough time, and this is a tried and tested model. In fact, on this particular thing, you can try to go for different number of neurons and different number of hidden layers and all those things, and see how it has performed. Obviously, it is going to take a lot of time, but for now, I have just copied this entire statement because I'll be doing a copy paste a bunch of time and I'll edit it. So this is convolutional 1, and now this is convolution 2 that I'm adding, where the input is 64 from the previous layer and the output is 128 this time. And then I'll take one more layer, that is going to be convolutional layer 3, that is going to take in 128, 250, 6. Convolutional layer 4, that is going to take in 256, 512. I'll just go for just one more here. Convolutional layer 5, it is going from 512 back to 1. So the discriminator layer here, you can see we have 5 convolutional layers starting from 64 feature maps that the network is going to learn, filter kernel for, then it is going to show up to it is going to go up to 512, and then of course at the end we just have one here at the end because this is our final output. It is going to be just one single number, that the index number which we train to be whether it is true or false, which is a real image or false image. Now we have batch normalization, that is self dot bn. I'll start with 2 because 1 would be already there. So I'll say nn dot batch norm 2d. That is going to be 128. Self dot batch norm 3 equal to nn dot batch norm 256. And lastly, self dot bn4 is equal to nn dot batch norm 2d and 512. Then I'll create the forward pass. I'll say def dot forward self comma x. This time I'm using leaky relu, f dot leaky relu, and I'm going to pass in self dot convolutional layer 1 with x and comma, I'm going to put a alpha value of 0.2. So it will have a slope of 0.2 in the negative direction. And similarly, I'll say x equal to f dot leaky relu is going to have self dot convolutional layer 2 x comma 0.2, then x equal to batch normalization over here x, then x equal to f dot leaky relu self dot convolutional layer 3 x comma 0.2, x equal to self dot bn 3 x, then x equal to f dot leaky relu self dot convolutional layer 4 x comma 0.2, then x is equal to self dot bn4, then that is going to return torch dot sigmoid last layer, that is convolutional layer 5 and x, and I'll flatten this out with -1 to 1. There you go. Let me run this. I'll say dnet. I'll create a class. Sorry, I'll instantiate this class and create an instance of dnet discriminator net. Then I'll take this y is equal to dnet, which by the way, it is expecting me to enter the some you know uh, torch here of some tensor here of torch dot random. Just I'm checking whether it is working fine or not. So random number 10 by 1 by 64 by 64. So 10 is the bed size, 1 is the grayscale image, 64 by 64 is the height and width of the image itself. Y dot shape, if you run it, I'm getting 40 by 1. It should be actually 10 by 1 if my memory serves well. Yeah, this has to be at the end 0. Okay, and this has to be 1. If you run this now you should get 10. Yeah, here what you have done, this would correspond to a sample size of 10, a batch size of 10 images. The one here, it corresponds to color dimension, and now we are creating this Gaussian to be monochromatic, that is so grayscale in this case, just one channel in the data, and this 64 by 64 is the image. And then the output of the discriminator, it is just single number for image, for each image that we input. Now let me create the class here of generator. Class generator net. That is going to be nn.module, and that here is def underscore underscore init underscore underscore self. That is over here. Then I'll say super dot underscore. So same process that we did before, just few tweaks that we have to be aware of. So this is there. Then I'll have the 5 convolutional layer, which I'm going to take as it is. I'll copy this as it is. But here there will be some changes, some minute changes. That is, we are having at the end a size of 100 because we have batch size of 100 here. So 100. Then now we are going down. So 5, 1, 2. This is 0 coming from the previous layer. This one here, it is 5, 1, 2, 2, 1, 6. Sorry, 2, 5, 6. And this is 256, comma 128, and 128 going to 64, and this here is 64, and rest of things it should remain the same. So here we can see we what a generator, a CNN generator looks like. Again, we start with some low dimensional output, so a randomly 100 select a randomly selected number. From here we are going to start expanding into image. So in this case we go from a 100 number, now we are going to go from a image resolution of 4 by 4 up to we keep doubling this. Eventually we'll get a resolution of 64 by 64 at the end. Now you can see that the depth of each CNN layer or the number of feature map also starts being very high. That is about 500 feature maps, and that is decreasing in this resolution. The resolution or the abstraction going down to basically to 1 over here. Implicitly, this is a 1 in here. Now, this is a generator network architecture. We have 5 convolutional layers starting from 64 feature maps that the network is going to learn, filter kernel for. And sorry, this one here, it should be 2 and 1. Otherwise, this will again be problematic. So we have, this one here at the end because this is our final output. It's just going to be a single number, which we train to be equal to true or false, which is basically real image or fact image. Then I'll have the batch normalization as well, which I'm going to copy. I'll copy this. Here, instead of 3 batch normalization, I would actually require 4. So right away, I'll copy this one more time and put it over here. Batch normalization 1 happens to be 512. This happens to be 256. This happens to be 128, 64. Then you will see def forward here, self, comma, x. Then I'll say same thing basically, which we have done here, right? The only difference is there's no ReLU function here. So what I'm going to do is rather than copying from there, I'll just say x equal to f dot ReLU, then self dot, I'll pass the batch normalization here itself and say self dot convolutional layer 1 x. Now take this thing, copy, paste here. This is convolutional layer 2 and BN2 here. Then this is 3, then 3 here. Then 4, then 4. Lastly, I'll say X here is torch dot 10h self dot convolutional layer 5x. And lastly, I'll return the X here. Okay, so uh, we have created this as generator and discriminator. Now what we are going to do is I'm going to input some random data. Uh, so this would correspond to a sample size of 10, a batch size of 10 images. I'll say that gnet, first I'll create the instance of generator net and the class that I've created. Then I'll say that y is equal to gnet, and then I'll pass in torch dot random number. So that will be 10 by 100 by 1 by 1. Then I'll say print y dot shape. Okay. And if you run that, you have error because let me see this, what happened. Kernel size 4 by 4, kernel size cannot be greater than the input size. Is that the case where we have done it? Return. Let me check this. What is happening here? Yes, of course, this has to be 1, right? And now run this. Hopefully this will again give me an error. Okay, so I made a actually very huge error here. This convolutional layer here, it is not 2D, it is transposed 2D, because remember we are doing a multiplication of the two tensor, right? So we cannot use it in this manner because as we have uh, we have to be aware that the convolutional layer 2D, if you're using this in the discriminator, then this has to be transposed 2D. So I'll just have to add in transpose here, as in, not just here, in fact everywhere. I'll copy this and paste here, paste here, here, and lastly here as well. And now if you run this, there you go, now it is working fine. However, we have to display this. I'll say plt dot im show, that is y 0 comma everything comma everything comma everything dot squeeze dot detach dot numpy, and lastly I'll say plt dot show. There we go. So we have created some input data. Now this would correspond to a sample size of 10, a batch size of 10 here. uh, One here, it is the color dimension, right? And 64 it is again the whatever we have, right? So this is what we're getting. Next is to train the model. For training the model, first I'll create the loss function, which happens to be nn dot bce loss. Then dnet equal to discriminator net dot to device. In case we use GPU, then it will put all this, the discriminator and generator that we have created is going to run that on GPU, right? So that is why we have to use that. Then gnet that we have used, it is going to be also generator net dot to device. Then I'll have to define the optimizer as well. So to optimizer, d dot optimizer is equal to torch dot optim dot atom dnet dot parameters. I'll keep a learning rate of 0.001 more 2. I'll define some betas as well, 0.5 comma 0. Almost 1. Then I'll do the same thing. This is the discriminator. Now we'll try to put this as a generator as well. So discriminator, and this is generator. Just put a G here and we are good to go. Run that. There it is. Then the number of epochs that we have to define, and we have to express them in the number of batches. So I'll say number of epochs is equal to, I'll say integer of 2500 divided by length of data loader. Okay, now if you check the number of epochs, this is 13. All right, so I've just divided, no, some length. I've tried to tone down this a little bit, right? So this is what I'm getting. You can keep, define any other epoch as well, but I do not want to be, running this notebook for too long, and thereby I have kept this as in this manner. That is, I have to factor in some sort of data loader here. Again, data loader, it is going to be something that will be, we can change it earlier as well, somewhere over here. So you can change the batch size similar, just maybe put a batch size of 50. And in that case, if you put a, I'll just try to put 50 here, let us say, right? So batch size here is not of 100 images, but 50 images. And if you create a batch size of 50, and then if you check the number of epochs, that would be just 6. So that is dependent on the batch size that you are defining, right? So thereby I'll put back to 100 for now, and thereby it is 13. More the batch size, more would be the number of epochs. Then I'll say losses is equal to empty list. Now I'll say I'll create one more empty list here. This is going to be this. I'll explain this what this is. Next is for EP in range number of epochs. I'll say for data comma nothing in data loader. Why? Because data loader will have the data itself and the label. So I'm just concerned with the data and not the label. So data, whatever the data that you have, I'm going to first right away put that to the GPU if you are using the GPU here, right? Then I'm going to create the labels for real and fake images. So I'll say real images, or should I say real labels. This is going to be torch dot once, since it's a real, and that is going to have some batch size comma 1 dot to device, and then this is fake labels is equal to torch dot zeros batch size comma 1 dot to device. Then next is to train the discriminator, right? For that, I'm going to say forward pass and loss for the real picture, and then forward pass and loss for the fake picture. So I'll say prediction of the real is going to be dnet, discriminator net to data, and then the losses of real is going to be loss function that you have created, which is going to take in the pred real comma real labels. This here is the output of discriminator. And this is what these are all labels. Basically, they are one. All right. Then I'm going to do the forward pass for the fake picture. So that is going to be fake comma data, right? So first I'll create the random number to seed the generator. I'll say torch dot random number, basically the same thing that I have used, but rather than a batch size that we have defined randomly over here, zero, sorry, not zero, rather 10. Instead of 10, I have to put the batch size, which is equal to the batch size that I have defined earlier. So this would be the batch size, right? And comma 100 by 1 comma 1. And that also I have to push to the GPU. Then I will say fake images that we have is going to be gnet, fake data that you have created. I'm going to feed it there. And that pred fake should be equal to dnet fake images. So this here is the, I'll just put a note here. This is random number to seed the generator. And this here, it is the output of generator. This here is the pass through discriminator. Then d underscore loss underscore fake is what I'm getting. This is going to be loss function again, which we have to pass through red fake comma fake labels. So here all the labels are basically 0. Then we have to collect the losses of both the real images and the fake images. I'll say d loss is equal to d loss fake plus d loss discriminator loss fake plus discriminator. So this is what this is, combined losses. Then the backprop, right? So backprop or back propagation is going to be rather simple. D, remember we are just talking about optimizer for now. We are not going to the generator, right? So optimizer, d dot optimizer dot 0 grad, then d underscore loss dot backward, then d underscore optimizer dot step. Then this is what we have trained the discriminator here. Remember, now I'm going to train the generator. So this is about training the generator here, which is going to be more or less the same. So I'll create this entire thing one more time. I'll copy this from here. By the way, this dot should not be here. Okay, so uh, this I will, actually it is not required. Okay, I'll, start afresh. I'll say this is fake images gnet.
So generate the fake images. So torch dot random number, batch size, comma 100, comma 1, comma 1 dot to device. Then spread fake images, that is going to be equal to dnet, then fake images. Then I have to compute the losses. Generator loss is equal to loss function that is going to have spread fake, comma real labels, and then I'll have the back propagation, but this time for generator I'll copy this entire thing, put over here, make some subtle changes. One is the generator, second here generator loss, generator optimizer. Then I'm going to take the losses that the empty list that I had created earlier. Remember this list that I've created? I'm going to put that and append it. Losses dot append using d underscore loss dot item g underscore loss dot item. Then I'll say d1 if the mean value of whether it is a predicted value of a real image that we have, if it is greater than 0.5, then we have to first convert that to floating number and then detach it. All right, then same thing for d2, but some difference. Torch dot mean spread underscore fake is greater than 0.5 dot float dot detach. And this entire thing I have to put that in the list that I have created and append it with as a list d1 comma d2. Lastly, I will print out the message that is going to say the epoch that we are under. Remember, we are under some epoch that we are working right over here, by the way. So I'll say message is just very simply, I'll put finished epoch is going to be epoch, sorry, not epoch, rather EP that you have plus 1 divided by number of epochs. And I'll say system dot std out if I'm not wrong, and then write the raw message as it is plus the message. Oh, actually, what we have missed out on, the reason I'm getting that underline is I think we have not imported the system as a library. So I'll import that as well. Import sys, right? So run this import system as well. And then this should not give me any underline. All right, you can see it has vanished. Now, lastly, I'm going to convert the performance from the list because currently I have it in the list. I'm going to convert that into array. So losses is going to be np.array. That is going to be losses. And that you have is going to be np.array. Pass in the entire thing that you have, that is d dot You have to first put that in the CPU, then convert into NumPy. And for every D in DEC, for every this and this, the list that you have created. I hope that it works well. If it doesn't, then we have to go back and fix many things. I have been very cautious. So let me run this over here. So before we have to run this, we have to go to change runtime and then turn on the GPU here and save it, go to runtime and run all one more time. Okay, you can see that it is running perfectly fine. So let it run for 13 epochs and then we'll continue. Okay, so we are finished training our model. Now let us create a smoothing filter. The job of the smoothing filter is to actually smooth out the curve that we are going to be creating in a moment. So I'm going to create a function that is smooth and that is going to accept two parameter x and k, and I'll put a default value of k as 15. And I'll say that this is going to simply return np dot convolve x dot np dot once, that is going to take in k, that is going to be number of ones it is going to create, and this should be comma here, and I will divide this by k to normalize it, and I'll say mode equal to same convolver, actually not convolve. All right, run that. Then I'll create the figure. First figure comma axis is equal to plt dot subplots, one row, three columns, fixed size is 18 by 5. That is going to be ax0 dot plot, and plot out what? Plot out the smooth, then losses, because losses, if you remember, these are the losses that I'm getting. So I'm going to grab all the rows and 0th column, and I will grab the first column here. So first one, that is over here, it is the discriminator, and this one is for the generator loss, so that we can compare both the things. And then I will say x0 dot plot, not plot, rather I'll say set x label batches, x0 dot set underscore y label generator loss. Then I will say that I have to turn on the labels as well. x0 dot set, not set, rather legend itself. First one, as I said, it is discriminator, comma, generator. You run that. There you go. So you have this discriminator and generator here. Then I will say x1 dot plot. This is losses. I'll say grab everything 5 to 0, and losses, I'll say grab everything 5. Well, it is actually not required for us, but still I'll plot this comma 1 And I'll say this is k dot. Yep, looks fine to me. This I'll say is dot set underscore x label. This is discriminator loss. And copy this as it is. And this one here is y label, but it is no longer a discriminator loss. It is generator loss. Then x2 dot plot. It's going to be smooth. Then this here, everything comma 0. I will copy this, paste here, and this is 1 here. Then I'll say x2 dot set underscore x label, then epochs, and 2 set underscore y label. Probability is real here. I have to actually put this in double quote. And this is x2 dot legend is one is real comma fake. So let us see what we have got. Okay, so I will just, yeah, I'll stop here. So remember, you're not going to see a lot of clear oscillation actually until but you still see over here, right? So here you start to see some of this oscillation here. The discriminator, the blue one, it is starting to do better, and then generator, it needs to, sorry, the discriminator is actually doing worse here, because the generator, it is starting to do better. You can see it is the losses, the generator losses, it is going to go down as the time processes. So as you start, discriminator, after a certain point, if your discriminator starts to do better, or discriminator starts to do better than generator, it is going to do the worse. Now here it looks like there's such a this over here it can see that maybe it's a negative correlation between the two losses from the two aspects of this model, because it is little kind of it is little bit of skewed by all this stuff happening over here. Now if you overtrain the GANs, you actually get reduced performance, and it looks like that we are starting to get into that regime over here as well. Now, if at around 2000 or maybe around 1200 batches even, right? So we are starting to see some of the divergence. After this point, it is starting to get, the two curves, that is the blue one and the red one or the orange one, it is starting to have some sort of divergence here, right? So and the last one, it is the output of the discriminator model. So what is this? What the discriminator is predicting as being real or fake is what we are getting here. Then you see that real images are being classified as real and the fake images are being classified as fake. And what you want is the fake images are not exactly zero. They should be higher than zero, because the discriminator is getting confused. The manifestation of training the model, or the drawback of the overtraining the model here, is that discriminator, it is getting really confused in this case. I mean, the values here, they are not super high, but the discriminator model is having a high time telling that it is what is real and what is fake. So that is why you are getting this kind of exaggerated graph over here. You can see it is kind of a, this one is quite going up and down after 1200 epochs. So this is what here. Again, this is an indication that we are perhaps overtraining our model. So maybe, but remember the uh, value that I have entered here, it is 2500 divided by some length of data loader. So maybe it should not be 2500, it should be around 1500, right? So that should be enough for us. But that is all in well. My model has, created some, it has done some learning and all that. But really, the thing that you are really do the GAN for, that is generative adversarial network, is because it generates thing, isn't it? So what we are going to do now is we are going to create some fake images, right? So I'm going to creating some generated fashions. So I'll say, first of all, gnet eval. I'm going to put my model into evaluation phase, and I'll say fake data that I'm going to create is equal to gnet, and then it is going to take in the torch dot random number. First is batch size, comma 100, comma 1, comma 1 dot to device. But then I have to convert this back to the CPU. Why? Because I have to put that in the after we have passed this into model, which happens to be on GPU, then I'll convert this back to CPU. Why? Because I have to run in matplotlib. So I'll say figure comma axis is equal to plt. Again, this is axis plt dot subplot 3 by 6, 3 rows, 6 columns. Fixed size is equal to 12 by 6. Then for every index comma axis and enumerate axis dot flatten over here, and that is going to x dot I'm show as fake data. Take that index and grab everything comma here dot detach dot squeeze comma cmap equal to grayscale, and I'll also turn on the axis as off, and if I run that, there we go. There we go. So you are, these are the fake images. These are not from the data set that is being provided to us after we have trained our model, basically creating the model, trained our model, we are now able to, generate this images. Now, if you run this as many times as you want, every time you are going to get some different image, right? So I'll put some title here, plt dot super title classes to focus, y is equal to 0.98, and I'll say plt dot show, right? So trouser, sneaker, pullover, the same thing that we have grabbed initially. Now, if I want to change it, for example, I want to take this classes to focus, right? Maybe trouser coat, maybe I'll take one more here. Instead of trouser, I'll put this one as ankle space boot. All right, and then run that one more time. No need to, well, we have to train actually our model because that has changed. But if you run this and then retrain your model and you come back, then it should be able to display some other images of the classes that you have chosen. You take more classes, it is going to take more number of classes here, right? So I'm just taking 3 here because that should be enough for you. At the end, I would say that it was quite a project, right? It was a difficult project, I can completely understand, especially if you do not have any background of deep learning and if you have not practiced it enough. right? So still it was my job to cover everything that was being promised, but this is difficult, but this is not it. Real life, I mean, these are just fake images, but still it's a grayscale images. Don't forget that in today's world, when Grok and Llama models, they are creating the fake images all over the time. Just understand how powerful those models are, right? And what, how many GPUs that is, required to run those model. This one here, it is very basic model that we have created. Now if this coding it is scaring you, I recommend you to go back and practice Python one more time, get your basics right and all those things. So that is, and this is exactly the reason that I said earlier that, Python, it is going to be, it is not going to be a linear process. You are always going to be, you're still, I'm still learning Python. You'll always be in the process of learning Python, right? But hopefully, this project was a good reflection of the capabilities of the deep learning models.